I
As in,
will.
most books are available online.
I know. Don't say that out loud. You're being recorded. It is say most books are available online. I'm pretty sure you don't mean legal copies, right?
Yes, sir.
So let's not talk about that, right? True, but unfortunately, many books will not have the same notation or the same background that the one as we are doing. So that may be a bit of a problem. Anyway, I will try to get assignments to you as soon as possible by this weekend, definitely. Okay. Okay. So any questions now? Have you been able to take a look at the last lecture that was uploaded somewhere around Wednesday or so? The one which had Burnside's method in it?
Yes, sir.
Okay. And anyway, even the previous ones, any questions from that? If not, I'm going to start by giving you a demonstration of using Burnside's method. I've already given one demonstration in the lecture itself, but that sort of is a rather simple situation. Things can make it trickier in other cases. So it's not as I perhaps oversold the method a bit when I gave the lecture. I said this is an algorithmic method where you can just start from basic group theory and just follow an algorithmic procedure, and without any additional calculations, you can find out the character table. Now, that is almost true, except that there are certain situations where the algorithmic procedure may not really work very nicely. You may need to go beyond just following that algorithm. You may need to carry out a few more steps. So, are there any questions about Burnside's method, or can I start with the example precisely? No questions about any that or anything else? Okay, fine. So let me just start with this. This is, of course, not relevant for you. It's an entirely different class altogether. But anyway, let's start with this one. Okay, so I will discuss Burnside's method in U application today. Now, this is just one method for constructing the character table for a group, but it is not the best method. In fact, there are further methods which are improvements on this. Okay. But the further methods require some more advanced mathematics, and so we are not going to discuss them in any detail right now. After all, the character table is very, very important. However, for most applications, you will already find the character table for the group under consideration, either noted down at the back of a group theory textbook or on the net somewhere. So you don't really have to calculate character tables from scratch most of the time. Sometimes you do, especially when you are when you're looking at some new system which may have a different symmetry group from the one that you had been expecting. You may have to start the work entirely from scratch. And there, methods like these become very useful. One advantage of methods like these is that they are algorithmic, so that they can put on a computer, and you can write a computer program, maybe using Mathematica or SymPy or something like that, which will actually calculate the character table given just the nature of the group elements. Okay. So what I wanted to talk to you about is basically an example of this method, a slightly more non-trivial example than the one that is there in the lecture video. That example is also actually non-trivial, although there we already knew the answer. So let us start with another case where we don't know the character table from beforehand. So this is the group which formally is called C4V. I'm going to describe the nomenclature later on, because the reason why a group is called like something like this is actually important, especially when you're talking about application of group theory to, say, solid state physics. These nomenclature actually convey some information. But for the time being, all we are really talking about is a symmetric group for a square. So we talked about the symmetry group for a triangle in the example. That was our favorite old group S3. But now we are going to talk about symmetry group for a square. So let's. So this is my square, at least as well as I can draw. And now the symmetry operations, let me just remind you. Reflection about this line, which is in a very bad location right now. So let me just try to draw it a bit better. So this reflection in the middle line here, this middle line here, through this diagonal, to this other diagonal, and then you have 4 rotations: 90 degree, 180 degree, 360 degree, and 270 degree, right? So symmetry elements E, A, B, which are these 2 reflections, C, D are these 2 reflections. Then you have F, which is 90 degree rotation, G, H. So G, of course, is square of F, a 180 degree rotation, and so on. We had actually met this particular example earlier. The only thing is we had not called this C4V then. And the conjugacy classes for this particular group is rather simple. It's an 8-element group, and the conjugacy classes are E is in one class. Now, reflections and rotations will never be in the same class, but all reflections are also not in the same class. The basic idea is 2 reflections will be in the same class if there is a symmetry operation which changes the plane of reflection, or in this case, a line of reflection, into the other line of reflection. That is, for example, if you're looking at A and B, there are reflections about this line and this line, that there is a symmetry operation which actually changes the reflection line for A into the reflection line for B, which is what? What does that? Which symmetry operation does that?
90 degree
90 degree rotation does that. In fact, the reflection C also does that. Okay. So basically, this says that A and B will be in the same class. You can actually find out which particular matrix will do the conjugacy. Oh, yeah. Okay. And then C and D will be in a different class. Again, C's line and D's line can be related to each other by a 90 degree rotation. That's definitely the case. Also, the important thing is A and C will not be in the same class because there is no symmetry operation which rotates this line into this line, right? 45 degree rotation is not a symmetry for the square. So AB is in one class, CD is in another class. G, the 180 degree rotation, is in a class by its own, and the 2 non-trivial rotations, 90 degree and 270 degree rotations, are actually in their same class. Okay. So let us just label these classes. We start by some arbitrary labeling of the classes. And the arbitrary labeling means you just have to number those classes. It doesn't matter which one you call 2, which one you call class number 3, and so on. But world over, everybody calls this class, the class with the identity alone, which every group has, as C1. Okay. I'm just going to follow a book. So I'm going to use the same labeling that a book uses. I'm going to call this one C2, this one C3, this one C4, and this one C5. A rather bad choice of ordering for us, but that's simply because I've written the classes first and then put in the labels according to a book which I'm using. So the way Burnside's method works is simple. You have to actually form the class vectors. That is, C1 vector, for example, is just E. C2 vector is F plus H. C4 vector is G. C5 vector is C plus D. Of course, when I say something like this, you have to remember that we are actually in the group algebra AG. That is, we have promoted the group, the underlying set in the group, which had these 8 elements, into the basis for a linear vector space. Our linear vector space consists of all possible linear combinations of these 8 symbols, E, A, B, C, D, G, F, G, H, multiplied by whatever numbers you want. This is, of course, an 8-dimensional vector space, and this is a space which carries the regular representation. That is one thing you have to remember. Okay. So notice that when you talk about the class C2, you imply this set with 2 elements F and H. When you talk about the C2 vector, you're talking of F plus H, and there is a distinction. The distinction simply can be obviously seen when you say form something like C2 into C2. Now, we have already discussed this before, but suppose I took the set FH and multiplied with the set FH. We have already defined long time ago when we talked about normal groups and so on, or quotient groups to be more precise, how to multiply sets with each other. So what is the idea? You take every element from the first set, pair it up with every element possible from the second set, and for all possible pairs, you just find the product. So if we are doing set multiplication, this will be FF, FH, HF, and HH, right? And FF, of course, F squared is what? F, remember, is a 90-degree rotation. So what is F squared?
G.
G. Fine. What is FH? 90 to 70. If you do the rotations one after the other, what do you get?
Identity.
Right. HF is also the identity, of course. And HH, which is a 270-degree rotation, if you do it twice, what do you get?
G.
Good. So this, remember, is a set, and in a set, multiple counts do not matter. So the product of FH times FH is actually GE. Okay. So you multiply these two classes, what you get is this, G and E, a set, which is not a class, by the way. Okay, but when you're doing this product for vectors, you're actually treating F and H as vector elements. F plus H is the sum of the 2 vector elements. So what you're really carrying out is this product, F plus H into F plus H. And very similarly to what we have done here, you are going to start with 4 terms. That is, you're going to get F square plus HF plus FH plus H square. And just as before, this is going to be G, this is going to be E, this is going to be E, and this is going to be G. But this is ultimately going to end up being 2G plus 2E. Note that this is an ordinary vector space addition, multiplication and addition. So that essentially all the standard rules of vector space are used, and G plus G is 2G. Unlike in a situation where I said where you have, if you have two occurrences of the element G, that's the same as one occurrence. And now notice that 2G plus 2E is actually a sum of class vectors, is twice times C1 vector plus, I've forgotten which one G was, C4. Now, the one important thing which I glossed over in the class was that I did not really, in the lecture video, was that I did not really give a proof that this kind of thing that you see here is generic. By which I mean that if you multiply two class vectors, the result, I stated that the result has to be something like this. The result has to be, so if I multiply Ci with Cj, the vectors together, the result has to be C1 into an positive integer, non-negative integer, plus C2 into a non-negative integer, and so on. That is, it's possible that some particular class may not be represented at all, so it will have a coefficient of 0. But if a class is represented, it has to be represented a whole number of times. So this is going to be sum over k, pk times numbers hij,k. So these hij,k's are non-negative integers. Okay, could be 0, but if they're not 0, they have to be positive integers. That's the claim. You saw that right now we did C2 dot C2 and found out that the result is 2C1 plus 2C4. So that of course tells me that H22, of course the two twos here, the first two twos come from this 2 and this 2. So 221 is 2, H222 is 0, H223 is 0, 224 is 2, and H225 is 0. So this is how you find out this small h, the class constants. Okay, I did not prove this result in the class, although I sort of gave an argument in favor of that. The basic idea is simply this, that I urge you to try to write down the proof mathematically properly. But the basic idea would be simply this, that if a particular element occurs in the product, say Ci dot Cj, let's say in this you have some element G. Okay. This is a bad notation basically because strictly speaking, Ci dot Cj is not a set. But what I'm saying is Ci dot Cj has some component in the direction of a particular group element G. If that happens, that means G occurs at least once there. What you have to prove is that if this is true, then every element which is in the conjugacy class of G occurs in this product. And if G occurs multiple times, maybe if a given element G occurs thrice, then every element in the conjugacy class has to come in thrice. It's a pretty easy thing to prove. Just use the definition of conjugacy classes, you should be able to get it. So if a particular element does not occur at all, then nothing else which belongs to the same conjugacy class will occur. But if a particular element occurs 5 times, then every element which is in its conjugacy class will occur 5 times. So we'll end up with 5 times the conjugacy class, the class vector for that particular element, plus other terms. Is this clear to everybody? Any confusions about this? Because this is the key step in this procedure.
So, sir,
Yeah.
sir, I mean, in this case, in this example, we have labeled these classes by E and I think A, B, and so. So you're saying if on the right hand side A appears some n number of times, then B also has to appear some n number of times, and similarly for all
Exactly.
other classes.
Exactly. So
Okay.
if in any product, say f occurs, after you multiply the thing out, if f occurs 5 times, then h will have to occur 5 times as well.
Okay.
And that's pretty easy to show. So I will ask you to figure out the proof of that. Okay. Yes. Remember exactly how you proved conjugacy classes, how you worked with conjugacy classes, and that will show you how the proof goes. But this is a central result. That is what you need as a basis for this method. In fact, that is what you need for a basis of lot else besides this method. Burnside's method is not really the only method available. There are many other methods available for dealing with character tables. Also, there are many other reasons why class vectors will become useful. So this particular result is actually very, very important. Even if you don't use Burnside's method ever, this would still be important. Okay. So let me just illustrate that in this particular case, at least. I'm not giving you a proof of this, but you should be able to figure out the proof in a pretty straightforward manner. So let me do one thing. Let me move this whole thing down a bit so that I can get some space to work. So what I will do is I will build up HIJKs for, okay, building up all the HIJKs will of course take a long time. So I'm not going to do that. That is precisely why I'm using a book today, or rather, not really a book, a piece of notes which I took from a book. But the reason why I'm using that is simply that since I will not be able to carry out the entire calculation in this class, it's just going to take way too long and be too boring for everybody. I will copy out the relevant small h's for the later parts. But at least let me show you how this goes for one particular I. And the reason why I'm focusing on one particular I is this. We defined matrices capital HI, one for each class. So this I, remember IJK, these indices run over 1, 2, 3, 4, and 5 in this example because there are 5 classes. These indices always run over the entire classes. So what I'm doing here is I'm defining an matrix capital HI whose jkth element by definition is HIJK. And these matrices play a central role in Burnside's method. Okay. So to find out the capital HIs, what you need to do is find out the small HIJKs. And that will give you capital HIs. Okay. So this is going to be an NC by NC matrix, where NC is the number of classes. In this particular case, all the HIs will be 5 by 5. And there are NC such matrices. In this case, 5 such matrices. Okay. Now, for one particular class vector, the small HIJKs and hence the corresponding capital HI is absolutely trivial. If you start with C1, notice the C1 dot C1, of course, is C1. What is C1 dot C5?
C5.
C5, right? Because in this case, it's just E dot C plus E dot D, and that's C plus D, right? In fact, in general, C1 dot any class vector is going to be that class vector back. And that actually tells you that for the identity, sorry. It tells you that for the identity at least, H1, of course, identity, remember, always belongs to first class, is actually the 5 by 5 identity matrix. That's pretty easy to figure out. And that is a general case. For the identity will always have this particular class matrix, which is going to be I5. Burnside matrix, which is going to be I5. Okay. So what about, let's try to, the non-trivial one is H2. Let's try to work that out. H2, For that, of course, what you need to do is multiply C2 by C1 to get H21 case, then C2 by C2 to get H22 case, and so on. And you will need to do all the 5 products. So C2 dot C1, sorry, let me just take this call. Nirmal. Sorry, year-ending crisis again. Anyway, so we have this. What we need to do is calculate C2 dot C1, which is of course C2, and that immediately tells me that the first row of H2 is a 5 by 5 matrix. What will the first row be? Can anybody tell me that? This is H21. Okay, let's call this K, 21K. Right? So what is the first row going to be?
Zero, 1, then 0, 0, 0.
So this one should be sort of easy to understand, right? All we are saying is C2 dot C1 is going to be sum over K, H21K, CK. And you can see that the only thing that you have on the right hand side is C2. That means H21, 2 is the only thing which is non-zero. It's equal to 1. Every other coefficient starting with I equal to 2 and j equal to 1 is definitely 0. So you get 0, 1, 0, 0, 0. C2 dot C2 we just calculated a while ago. And C2 dot C2 came out to be? So can anybody tell me what this is going to be?
20020.
So it's going to be 2, 0, 0, then 2, 0. Right.
20.
1, 2, 3, 4. The fourth index is 2 and then you have 0. Fine. Now C2 dot C3. This one requires a bit of a non-trivial calculation. Can anybody tell me what FA is? Sorry. Ball. আচ্ছা শোন তুই আমাকে একটু পরে ফোন কর, দুটোর পরে ক্লাসে আছে। Okay, so what you need to do is carry out the products F times A, H times B, and so on. Okay? And if you do that, okay, let's just point out that if you started with a point here, let's say this point, and did F times A, where would it go? If you first did F times A means you first do A, that means you reflect in this line, so it goes here, right? Then you do F, which is a 90-degree rotation. So if you rotate this thing through 90 degrees, it will end up somewhere here. Right? So can you tell me what operation will take this, the starting point here, directly to this?
C.
C. So FA is C. And going that way, you can figure out what all the four are. In fact, it will turn out that in the four products, two of them are actually C and two of them are D. Okay. It's sort of easy to understand in a way that this is going to happen. Because first of all, once C is there, what we said was D has to be there, right? C and D are in the same class. So every class has to come in, class element has to come in twice, coming together. So if you have C, you also have to have a D. Now, what you will find is H times B is also equal to C. And because H times B is C, that means C occurs twice, D also occurs twice, and that's it, because you have only 4 terms here, right, when you multiply. So this thing has to be 2C5. So this product matrix is going to be, or this matrix here, H2, the third row for that will be what? Can anybody read that off for me?
0, 0, 0, 0, 2.
Good. Fine. Now C2 dot C4. You multiply this by this. Can you tell me what that is going to be? This one is very easy.
You'll get C2 itself.
You're going to get C2 itself. Why? Because when you multiply G by F, that's a 180-degree rotation and a 90-degree rotation. That together gives you 270. So that gives you H, right? But once you have H, you don't even need to calculate the other one. The other one has to be F. Because if H is there, F has to be there. So C2 dot C4 is C2. So 0, 1, 0, 0, 0. And the final line, C2 dot C5. Any guesses what this is going to be? You don't even have to guess. You should be able to figure it out pretty easily from what we have done here. Just find out one factor, that should be enough.
C3, 2C3.
Yeah. Because, well, a 90-degree rotation followed by a reflection essentially is going to be another reflection. That's going to be F times C is going to be something either A or B. And once you go from there, it's pretty easy to show. Of course, you can calculate the whole thing out, but it's pretty easy to show that this has to be twice C3. So this is going to be 0, 0, 2, 0, 0. So that is how you find out H2. Now, I'm simply not going to bore you with working out all the H's. There are 5 H's. One of them we already know, the identity. Then we have 5 more, 4 more. More now, I found out 1. So let's just do one thing. Let's copy this one out. So that's my H2. Now I'm going to refer to my notes and copy out H3, H4, and H5 for you. The first line in H3 is trivial, right? It's C1, C3 star C1. That has to be C3. So it has to have this. And so on. The other lines are also pretty easy to figure out. So it's really not very time consuming. I just don't want to bore you with working out everything. But I will need the matrices. So 0, 1, 0, 0, 0, 0, and 0, 0, 2, 0, 0. So that's what H3 is. H4 works out to be . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Now, I think the book which I copied it from seems to have an error in it. Because H4, the first row, has to be due to C4 star C1, that has to be C4. And so it has, the first row has to be 0, 0, 0, 1, 0. My book says that's H5. But that's impossible. The first row, of course, is the product with the identity class, so that has no other choice. Okay, now that puts me in a bit of a quandary because now I am not sure whether the other lines are also correct. So let me quickly check. The second line, C4 star C2. Let's go back to the classes. C4 is just this. And C4 star C2, what is that going to be? We already know that because we forgot what C2 star C4 is.
C2.
It is going to be C2. So the second row has to be 0, 1, 0, 0, 0. And that, it seems that there is a typo in my, now it's worse than before because my book actually says 0, 0, 0. Oh, my book seems to have mixed up H4 and H5. That's not that bad. 0, 0, 1, 0, 0, 1. Not too bad, right? I think this is H4. This is what my book calls H5, but this should be H4, and what my book calls H4 should then be H5. At least the first row definitely agrees to that. By the way, working out these products is not really as much work as I have made it out to be, because when you have calculated C2 star C4, you have also calculated C4 star C2. Now, this is also another result which is not really obvious. Group products don't commute, but class vector products do. This is something which you have to figure out again. The proof is pretty straightforward. That if you multiply Ci with Cj, you get the same as what you get when you multiply Cj with Ci. So basically, many of the, when you get to the later matrices, much of the multiplication has already been done for you. For example, if you come to H5 at the end, all the products you need have already been done before. So it's really not as much work as I made it out to be. Okay. So apart from the minor hiccup that my book seems to have mixed up H4 and H5, I'm pretty sure of that by now. These are the five matrices. Of course, the fifth one has not been written. That's H1. That's of course the 5x5 identity matrix. Now, the reason why we are interested in these five matrices is that the Dirac characters. Now, I hope people have at all had time to look at the video, right? Because if you don't know if you have not looked at the video and I keep on talking about Dirac characters, that may be simply a waste of everybody's time. So if you have not seen the video yet, the last one, please let me know now. Anybody? If all of you have, then it's fine. So since there seems to be no voice coming up which says no, I'm going to assume that everybody who is here at least has taken a look at the last video, so you know what Dirac characters, etc. are. So basically, these Dirac characters can be written down as a column vector, and that column vector is going to be that column vector, if not that column vector. The Dirac character, the column vector basically has one column vector for each irrep. And since you have 5 classes, you have 5 irreps. So 5 classes, 5 irreps, 5 column vectors, each of which are simultaneous eigenvectors of H1, H2, H3, H4, H5. So in principle, if you diagonalize H1, H2, H3, H4, H5, you have found out simultaneously, you have found out all the eigenvectors, simultaneous eigenvectors, and from them you can immediately read off what the Dirac characters are going to be. And once you have found the Dirac characters, you can easily use them to find out the class characters, the one which we really will put in the character table. Now, the reason why I'm showing you this is that in this case, finding out the simultaneous eigenvectors takes a bit more work than in the example that I gave in the class. Well, one thing should be obvious. Although it's really rather non-trivial to prove it ab initio, if these vectors have a bunch of simultaneous eigenvectors, and they can all be simultaneously diagonalized, then what can you say about their commutation properties?
They commute with each other.
Okay, they commute with each other, which may not be so obvious from the definition, but that's the result which follows essentially using group representation theory. Okay, so if you can find a diagonalizing matrix which diagonalizes one of them, will that necessarily diagonalize the others? All these matrices commute, right? So if I find a matrix which diagonalizes, say, H3, will that necessarily also diagonalize H2, H4, H5, H1?
No.
Why not?
I was thinking of the H1 matrix, like any matrix, like H1 is
Good.
already
That's actually a wonderful argument. Just look at H1, which is the identity matrix. That's already diagonal. And not only that, you can multiply it by any matrix on the left and its inverse, any invertible matrix on the left and its inverse on the right. And what you end up with is that it stays diagonal. So if you look at H1, whatever matrix diagonalizes it gives you no information whatsoever about a matrix which will diagonalize the others, because every invertible matrix will diagonalize H1. In fact, of course, it is already diagonal. So it's not only already diagonal, it commutes with every matrix. So it will automatically be diagonalized by everything. Now, this has actually quite this is a very important point, because not only because of this particular method, but because in quantum mechanics, this issue occurs over and over again. I'm not saying that this particular method has anything to do with quantum mechanics, but it's the same math. That is, if two operators commute, it's not necessary that the eigenvector of one will be the eigenvector of another. Just hold on. Yes, Ritesh. Okay, sorry, I have to keep on attending to these urgent calls today. Oops, not really relevant. So, as I was saying, if you want a simultaneous diagonalizer eigenvector, the problem really lies with the degeneracy of the eigenvalue. You know that if you have an eigenvector of an operator A or a matrix A, the same math, corresponding to a non-degenerate eigenvalue, then it has to be an eigenvector of the other matrix which commutes with it. I hope everybody is aware of that, right? This is a very critical thing also in quantum mechanics. So I hope everybody knows this, that if A and B commute and you have a non-degenerate eigenvalue of A, then any eigenvector corresponding to that non-degenerate eigenvalue has to be an eigenvector of B as well. But if there is a degeneracy in the eigenvalue of A, then it is not guaranteed that any eigenvector of A corresponding to that eigenvalue will be an eigenvalue of B. Right? Is this something which everybody here knows? Or
So, sir,
yeah.
so sir, you are, I mean, imposing an additional condition that all eigenvalues have to be like distinct. That is the extra condition that you're imposing.
No, I'm not imposing any condition right now. All I'm saying is, if you look at a particular eigenvalue, I will get there in the long run. That is what I'm going to get to in the long run. The trouble will be that let's forget about this particular bunch of matrices right now. Let's talk about a general scenario. If you have two operators which commute, or what is the same thing mathematically really, if you have two matrices which commute, what can you say about the simultaneous eigenvectors? This is going to be very important for this particular calculation, but this is also very, very important in quantum mechanics in understanding simultaneous measurability and stuff like that. So if two operators commute, then they can have simultaneous eigenvectors. But what people often confuse with this is a statement that if two operators commute, then they must have simultaneous eigenvectors. Or, which is also perhaps true if you interpret the must in a particular way. But if you imagine that any eigenvector of A is automatically an eigenvector of B, then that of course is wrong. If there is no degeneracy in a particular eigenvalue, then the eigenvector of A corresponding to that eigenvalue is automatically an eigenvector of B. But if the eigenvalue is degenerate, then suppose a particular eigenvalue is twofold degenerate, right? Then what happens? Let's say the corresponding eigenvectors are x1 and x2. That is, ax1 is lambda1 x1 and ax2 is lambda2 x2. Now, what can you tell about bx1 and bx2 then? Okay, let me just write this down, perhaps. I have two matrices. Let's take two matrices, A and B commute. And let's say you have ax1 is lambda x1, ax2 is lambda x2, and x1, x2 are not proportional to each other. So they are linearly independent vectors which correspond to the same eigenvalue lambda. So lambda is twofold degenerate, let's say. Then what can you say about bx1? And bx2? If say ax were lambda x and lambda is non-degenerate, then what you can immediately say is bx also has to be mu x. That is, x has to be an eigenvector of B for some eigenvalue mu. But in this case, in the degenerate case, what can you say? What can you say about bx1?
It will be a linear combination
Of what?
x1 and x2.
Exactly. What you cannot say is bx1 is going to be something times x1, but what you can definitely say is this. And similarly, what you can definitely say here is b21 1 plus b22 x2. I hope this is something which everybody is aware of, and you should know the proof of this. Because this is a very important thing also in quantum mechanics. It's a very important result in linear algebra, but it's physically useful in quantum mechanics. What this of course tells you is that you can actually diagonalize or find out eigenvectors of capital B by taking appropriate linear combinations of x1 and x2, and for that you have to just solve a 2 by 2 matrix eigenvalue equation. In fact, the eigenvalue equation for this matrix B11, B12, B21, B22. You find the eigenvalues and eigenvectors for this matrix. That will tell you what the eigenvalues and eigenvectors for capital B are. At least we'll give you two of those eigenvectors. Okay. But the point really is that if an eigenvalue is degenerate, then its corresponding eigenvector, first of all, is not unique. You could start with x1 or x2 as eigenvectors, or you could start with any any non-singular combinations, linear combinations of x1, x2, and call that your eigenvector. That would still work. And as a result, it's not guaranteed that any matrix which diagonalizes A will automatically diagonalize B. Okay? So, following through with this, if you found a matrix for which all the eigenvalues were distinct, that is, there is no algebraic multiplicity at all, then there will be no degeneracy in any of the eigenvectors, and any matrix with any diagonalizing matrix for this particular matrix will automatically diagonalize all the others. Is this clear to everybody? Yes? Any confusion about this? So, in our example that we talked about in the class, in the lecture video that is, we talked about S3. S3 had three classes. So we would get three capital H matrices. And these three matrices will all be 3 by 3 matrices. Okay. And one of them was, of course, the identity. And while it is the simplest, it's also completely useless as far as finding out simultaneous eigenvectors is concerned, for the simple reason that any vector is an eigenvector of the identity matrix, right? Any non-zero vector is. So this gives you absolutely no information about simultaneous eigenvectors for H1, H2, H3. There, H2 happened to have two eigenvalues, two distinct eigenvalues. That is, one eigenvalue was twofold degenerate, and hence, even if you tried diagonalizing H2, there is an ambiguity in the diagonalizing matrix, and any matrix which diagonalizes H2 will not automatically diagonalize H3. On the other hand, H3 had three eigenvalues, each of which were distinct. As a result, no repeated eigenvalues. All of them would have to correspond to independent eigenvectors. And now you can uniquely find the diagonalizing matrix for H3, which will automatically diagonalize H2 and H1. Is this issue clear with everybody? Or have I lost somebody with this?
So could you just repeat, how diagonalizing S3 will diagonalize H2?
The point is, first of all, when you say matrix diagonalizes, say, let's talk of A and B. If SA, S inverse is diagonal, or rather S inverse A is diagonal, let's put it this way. What do you know about S or columns of S? Are
Eigenvectors of A.
right. So now if S diagonalizes both A and B, of course the diagonal versions will be different, but it diagonalizes both A and B, then S is also, if the columns of S are also eigenvectors of B, right?
Yes, sir.
Now, if A happens to have distinct eigenvalues, which leads to the conclusion that none of the eigenvalues of A are degenerate, right? Then any eigenvector of A is automatically an eigenvector of B. Is that particular point clear?
Yes, sir.
Or a non-degenerate eigenvalue of A, the corresponding eigenvector of A has to be an eigenvector of B. So if A has three distinct eigenvalues in this case, A is 3 by 3, so it can have at most three distinct eigenvalues. If it does have three distinct eigenvalues, then, okay, I'm talking about the 3 by 3 example here. Well, it could be 5 by 5 in our case right now. But anyway, let's stick to S3, where we have 3 by 3 matrices. A is 3 by 3. If it has 3 distinct eigenvalues, each of its columns are not only eigenvectors of A, they have to be automatically eigenvectors of any matrix which commutes with A. So eigenvector of B, eigenvector of C, whatever. Okay. So in the example that we talked about in the lecture video, that was actually the example. You had 3 classes, 3 by 3 matrices, and of them H3 happen to have 3 distinct eigenvalues. So if you diagonalize that, you immediately find a matrix which is not only going to diagonalize H3, it is going to diagonalize H1 and H2 as well. Is that clear to everybody? Yes?
Yes, sir.
On the other hand, diagonalizing H1 obviously does not tell you anything about diagonalizing H2 or H3, because every invertible matrix diagonalizes H1. Way too much degeneracy in the eigenvalue. H1 is identity, so the only eigenvalue is 1, 3-fold degenerate. Every vector is an eigenvector. Every non-zero vector is an eigenvector. Okay, H2, 2 eigenvalues, one of them 2-fold degenerate. So although one column vector, the one corresponding to the non-degenerate eigenvalue, is definitely a common eigenvector for all the 3 matrices, the other 2 are not guaranteed to be. So diagonalizing H2 does not immediately diagonalize H3, but diagonalizing H3 does. But unfortunately, the point is, if you could find one of these H matrices which has all distinct eigenvalues, then just find diagonalizing that one matrix will work out for the whole set. Okay. However, in this particular example that we have, the example of C4V with these 4 matrices, the trouble is, for all of the 4 matrices, the eigenvalues are actually, you don't have, okay, rather let's put it this way. None of the 5 matrices, I'm saying 5 because that's identity also. For none of the 5 matrices do you have distinct eigenvalues only. For H2, the eigenvalues are pretty easy to fit. In fact, the eigenvalues of, let's say, H4 are pretty obvious. Can you tell me what they are?
C2 and C5. Yeah,
I hope you can see this clearly. Let me just erase this one term which is written a bit badly and written properly. It should be rather obvious that this one, and this one, which are sitting at the diagonal positions. But just because they are on the diagonal positions is not important. The point is, if you look at this matrix, you can see that these 3 essentially will correspond to 1 with zeros everywhere else. That means if you apply H4 on a vector, you've got just that. On the second basis vector, you've just got the second basis vector. H4 acting on the third basis vector, you've just got the third basis vector back, and so on. So the second basis vector is of course 0, 1, 0, 0, 0. That's an eigenvector corresponding to eigenvalue 1. 0, 0, 1, 0, 0 is an eigenvector corresponding to eigenvalue 1 again. 0, 0, 0, 0, 1 is an eigenvector corresponding to eigenvalue 1. These 3 have eigenvalue 1. Basically what this says is H4 acting on the first basis vector, H4 acting on E1 gives you E5. That's what this column is telling you. Sorry, E4. And H4 acting on E4 is going to give you E1. So these are not eigenvalues, not eigenvectors. All the others, E2, E3, E5 are. Can you tell me what are the corresponding? Of course, that means E1, E4 is an invariant set under the action of H4. You don't go outside that. So E1 and E4 can be linearly combined to find out eigenvalues, eigenvectors of H4. But can anybody tell me what the eigenvalues are here?
1 and minus 1.
1 and minus 1 should be, of course, this is nothing but sigma 1, right? The matrix. And so eigenvalues here are 1 and minus 1. That means 4 of the eigenvalues are plus 1, 1 is minus 1. A very high degree of degeneracy, diagonalizing H4 doesn't tell you anything. Oh, just tell you something, just not everything. And H2, H3, H5 happen to have exactly the same eigenvalues. And it takes a bit of work to work out those eigenvalues, but not too much. The eigenvalues happen to be -2, -2, 0, 2, and 2. Just quoting the values, I think anybody should be able to calculate and determine these eigenvalues. All these three, H2, H3, H5, has these eigenvalues. Okay. So the problem we have is that this does not give me enough non-degenerate eigenvalues to play with. H4 had -1 and 4 ones. Okay. And this one has 2 -2s, 2 + 2s, and 1 0. Now, it might, despite that, it might be possible. Okay, for example, if you look at H4, you are sure that one eigenvector for this H4 is actually an eigenvector for all the other matrices as well. Which one is that? Or what eigenvalue does that correspond to?
-1.
The -1, right? Because that's the one which has no degeneracy at all. And so -1, the eigenvector for -1 is definitely going to be eigenvector for H2, H3, H5, and so on. So I've got at least one eigenvector get simultaneous, which is good. Well, for H2, H3, and H5, there is one eigenvector which is definitely an eigenvector for all the rest. Can anybody tell me which one that is?
So
Which eigenvalue is that? Yeah, sorry, you said something
Yes, sir. I mean, could you repeat the question?
Like for H4, the eigenvector corresponding to -1 is definitely an eigenvector not only of H4 but also of all the other three. Okay? Is that clear?
Yes, sir.
If you start, if you apply 1, 0, 0, -1, 0 on this matrix, it should be pretty easy to see that what you are going to get is actually, okay, what are you going to get when you apply this matrix on 1, 0, 0, -1, 0?
We'll get -1 as eigenvalue.
You are going to get, this is an eigenvector corresponding to the eigenvalue -1. Fine. And this is definitely an eigenvector for all the other matrices as well. Okay. Now, for H2, this is the spectrum. These are the eigenvalues. So one eigenvalue is non-degenerate, right? 0 is non-degenerate. Agree?
Yes.
Okay. But now, if that could have given the eigenvector corresponding to that definitely is an eigenvector for everybody. Okay. So how many such eigenvectors can I find this way? I need 5 eigenvectors. Can I find 5 this way? H1 is no good at all because everything is an eigenvector, doesn't matter, and eigenvalues are completely degenerate. H4 has at least given me one eigenvector which will be in the simultaneous diagonalizing matrix for every one of them. And why am I so interested in that? Because the columns of that will give you the elements of that column will actually give you the Dirac characters directly. So at least one set of Dirac characters I found out, 1, 0, 0, minus 1, 0. But what about this eigenvalue? How many eigenvectors can this give you?
One.
One, well, it's possible that it will give you 1 for H2. H3 is a different matrix, right? It may have the same spectrum of eigenvalues, but it's possible that that particular eigenvector will give you a different, particular eigenvalue 0 corresponds to a different eigenvector. Is that possible? Is that possible, at least in principle?
Yes.
So, in principle, at least it might seem that H2, H3 and H5 can give you one eigenvector each. H4 has already given you one, so at least you have 4 of the columns of S4. Actually, no such thing happens. If you tried it out, you would see that this one, which is the eigenvector corresponding to eigenvalue minus 1 for H4, is also an eigenvector corresponding to eigenvalue 0 for H2, H3 and H5. So the non-degenerate eigenvalues that all these matrices have together give you no other information whatsoever. Just gives you one eigenvector, nothing else. Okay? So what I'm trying to say is, trying to find a simultaneous diagonalizing matrix, which means a bunch of simultaneous eigenvectors from these matrices, looks problematic, because the only vector that is guaranteed automatically to be a simultaneous eigenvector of all of them is 1, 0, 0, minus 1, 0, and that is the only one you can talk about without any confusion. Right? So now, any suggestions as to how you can proceed? This is the reason why I brought up this particular example. This is something which I want you to sort of appreciate, that Burnside's method may not be that obvious a method to use always. Otherwise, you wouldn't have ever learned any other method. You would have just learned one method and that's it. But can anybody tell me how I can proceed here? Like how I can find out simultaneous eigenvectors? Yes? Okay, let me just ask you this. Suppose you have a matrix X, which a column vector X, which is an eigenvector of A and B, simultaneous. Is this an eigenvector of A plus B?
No, in general.
No.
No. Are you sure?
Yes, it is.
Yes, it is.
Lambda
It is
plus u.
actually.
Lambda plus
Right?
mu.
Lambda plus mu x. Okay. So the important point is, if I make now, in general, if you add up in general, this kind of thing, if you add up two matrices, you cannot say anything about the eigenvectors of the sum matrix from the eigenvectors of the original matrix. But if two matrices happen to have a simultaneous eigenvector, then that is an eigenvector also of the sum. In fact, it is an eigenvector not only of the sum, it's an eigenvector of, say, C1 times A plus C2 times B. Okay? Clear? Is this clear to everybody? This is something which is very trivial, but this is something which people tend to forget. So, while what we are really seeking are simultaneous eigenvectors of H2, H3, H4 and H5, and the stumbling block here is that the eigenvalues are so strongly degenerate that they don't really give you much information, except that they have only yielded one eigenvector which is simultaneous. Okay. What we can do is form linear combinations. That is, say for example, let's try H2 plus H3. The eigenvector which is simultaneous will definitely be an eigenvector also of H2 plus H3, right? And so you can, and now explore what the eigenvectors of H2 plus H3 are. In fact, but more importantly, explore their eigenvalues. You will be able to find more non-degenerate eigenvalues doing this way. I'm not saying only H2 plus H3. I'm saying take any two of them, add them together, find the corresponding eigenvalues. And if you have a degeneracy in the eigenvalues, check whether you have found out a new eigenvector corresponding. If you don't, if you have a non-degenerate eigenvalue for this combined matrix, that is going to give you a simultaneous diagonalizing simultaneous eigenvector for all the 5 matrices. Is the point clear? So you do this not just from one set of class matrices, you do it from all the class matrices. That is, instead of H2, let's consider H2 plus H3. That's a new 5 by 5 matrix. Find out its eigenvalues and eigenvectors. That may give you more non-degenerate eigenvalues, and now that you have more non-degenerate eigenvalues, you can find out more eigenvectors. That's simple as that. Okay. By the way, 1, 0, 0 minus 1, 0 is guaranteed to be an eigenvector for this. Okay, I'm not looking at that. That one is known already. In that, I know that that will correspond to eigenvalue of minus 4. Sorry, eigenvalue of 0. Right? Because H2 acting on this vector give you 0, H3 acting on this vector also give you 0. So H2 plus H3 acting on this vector will definitely give you 0. I'm not looking for that one. But apart from 0, you find any other non-degenerate eigenvalue, use that. That will give you an eigenvector which is new. And by forming such combinations, you don't need to do it very many times, pretty fast. You should be able to find out simultaneous diagonalizing eigenvectors. So this is your homework, by the way. So one of the reasons why I did not make up the assignment, apart from being busy with everything and so on, was also that I wanted to discuss this thing here so that I can, well, fairly give you the rest of the calculation to fill up. So this takes a bit of effort, not too much, and I would suggest that it may be handy to learn at least how to find out eigenvalues using, say, the SciPy module. So is this okay with everybody? Any questions? So I've told you what the next assignment is. I will print it out and give it to you over the weekend. But this is basically your next assignment. Use Burnside's method to find the character table for this particular group, the symmetry group of a square, where you have to exercise a bit more effort just beyond finding out eigenvalues and eigenvectors of the 5 matrices. You may need to find out eigenvectors, even you will need to find out eigenvalues and eigenvectors for some integer, some combinations. Typically, just adding up H2, H3, H2, H4, etc. will be enough.
Sir,
Go ahead. Yeah.
Sir, in the H3 matrix, C3 dot C4 and in the H4 matrix, C4 dot C3 will be same, but in these two matrices they are not same.
Okay, let's see C3.C4. If you're saying that, then that's definitely true. Let's check C3.C4. That would be the fourth row, right?
Yes,
Fourth
sir.
row is saying 0, 1, 0, 0, 0. That's, of course. Okay, these matrices may very well be wrong because, as I said, I found out that the matrices are wrong anyway. So then I just imagine that they are just mixed up the two matrices, but they may have mixed up more than that. Let's just see. H3 times, let's see whether what you're saying is right. C3 times C4. What this is telling you is C3 times C4 will be the fourth row of the H3 matrix. This is telling you that C3 times C4 is C2. Right?
Yes, sir.
And C4 times C3, should that also be C2? Let's see what this is telling you. C4 times C3 is
C3.
C3. So let's just check whether that's right.
Sir, I just worked it out. It is coming out to be C3 for both.
It's coming out to be C3 for both. Right?
Yes, sir.
So that means this one is wrong. Right.
H3,
So
yes, sir. H3 matrix.
H3 is wrong. This one is not 1. It should
Yes,
be 1
sir.
here.
Yes, sir.
But that means the last column would also perhaps be wrong.
Yes, sir.
I think there should be 2 here.
Yes, sir.
Did I copy it wrong? No, I didn't. I didn't copy it wrong. I think they have copied it wrong.
And the third row, sir, also is
I
coming
think,
out to
yeah.
But
So please don't rely on these at all. What I guess is what has happened is, although they use this particular ordering C1, C2, C3, C4, C5, they wrote down the ordering, maybe they used some other ordering actually during the calculation, and they forgot about that when they labeled them. Which is, H2 seems okay. So,
yes, sir.
okay.
All the other matrices are fine. Just H3.
H3 seems okay. And H4 in the book, this was called H5, this was called H4. That was my first, and that was obviously wrong. So we could easily check that out. But H3, yeah, you're right. This definitely is wrong. So your
Right.
assignment, of course, involves calculating these matrices from scratch anyway. But that's a small part. That actually is not the most work. Okay, thank you for that. That would be pretty useful. And that should be useful for everybody. Okay, so any further questions? And that should teach me not to trust a book and work it out myself first. I was being a bit lazy and tried to copy it out from a printed text. Printed texts are not necessarily Bibles, so, or even if they are Bibles, they may have mistakes. The Bible definitely has. So, yeah. Anyway, any further questions? If not, let's wrap up this class. And so I've already told you what the assignment is. The assignment will be put up on VLearn soon, but you can start working on it from right now.